Hello everyone, welcome to my YouTube channel. This is Pooja pursuing BE in Sri Venkateshwara College of Engineering. My USN is 1VE23AC092, studying in second semester, section Infinity, course name Mathematics 2 for EEE stream, course code BMATE201. In this video, we'll be seeing about vector integral errors in finite precision. The computation of vector integrals in finite precision arithmetic can be prone to various numerical errors that can significantly impact the accuracy and reliability of the results. Understanding the sources of these errors and developing techniques to mitigate them is crucial in many scientific and engineering applications that rely on precise vector integral calculations. Introduction to vector integrals. Definition. A vector integral is a generalization of the scalar integral to vector valued functions. Instead of integrating a scalar field over a domain, a vector integral integrates a vector field over a surface or volume, resulting in a vector valued output. The importance. Vector integrals are fundamental in many areas of physics, engineering, and mathematics, such as fluid mechanics, electromagnetism, and differential geometry. They are used to calculate quantities like flux, circulation, and work, which are essential for understanding and modeling complex systems. Applications. Examples of applications that involve vector integrals include calculating the total force exerted on a surface, determining the total electric flux through a closed surface, and finding the work done by a force field along a curve. Truncation errors. Vector integrals often involve approximating continuous functions with discrete representations, such as using numerical quadrature techniques. The truncation of these approximations can introduce additional errors that can compound the overall numerical error in the final result. Third one, conditioning. The structure of the vector field and the geometry of the integration domain can lead to ill conditioning, where small changes in the input can result in large changes in the output. This can make vector integral computations highly sensitive to numerical errors. Rounding errors. Floating point representation. Computers represent numbers using a finite number of bits, leading to a limited range and precision. This can cause rounding errors when performing arithmetic operations on these numbers, as the true result may not be exactly representable in the computer's finite number system. Accumulation of errors. In the computation of vector integrals, rounding errors can accumulate through multiple arithmetic operations, such as those involved in numerical quadrature or vector field evaluations. This can result in significant deviations from the true integral value, especially for complex or high-dimensional integrals. Mitigation strategies. Techniques to mitigate rounding errors include the use of higher precision arithmetic, such as extended precision or arbitrary precision libraries, as well as the development of specialized algorithms that are more resilient to these types of errors. Truncation errors. Discretization. Vector integrals often involve the discretization of continuous vector fields, such as using a finite set of sample points or a grid-based representation. The mismatch between the continuous and discrete representations can introduce truncation errors that depend on the accuracy of the discretization scheme. Numerical quadrature. Numerical quadrature techniques, which approximate integrals using a finite set of function evaluations, can also introduce truncation errors. The choice of quadrature rule and the number of sample points can significantly impact the accuracy of the vector integral computation. Geometric approximations. When the integration domain has a complex geometry, it may be necessary to approximate the domain with a simpler discretized representation. This geometric approximation can lead to truncation errors that depend on the accuracy of the representation. Convergence analysis. Analyzing the convergence of the numerical scheme as the discretization is refined is crucial for understanding and mitigating truncation errors in vector integral computations. Quadrature techniques. Gaussian quadrature. Gaussian quadrature is a powerful technique for evaluating integrals with high accuracy by strategically choosing the sample points and weights. It can be extended to vector integrals by applying the method component-wise to the vector field. Adaptive quadrature. Adaptive quadrature methods dynamically adjust the number of sample points and their locations based on the behavior of the integrand, allowing for more efficient and accurate evaluation of vector integrals, especially in the presence of high frequency or localized features. Composite schemes. Composite quadrature schemes, such as the trapezoidal rule or Simpson's rule, divide the integration domain into smaller subdomains and apply a simple quadrature rule to each subdomain. This can be effective for vector integrals with smooth or well-behaved vector fields. Error estimation and bounds. A priori error bounds. Developing a priori error bounds which provide estimates of the numerical error before the computation is performed can help guide the choice of discretization parameters and quadrature techniques for vector integrals. A post-priori error estimation. A posteriori error estimation, which provides error bounds after the computation is complete, can be used to assess the accuracy of the results and guide further refinement or recomputation if necessary. Convergence analysis. Analyzing the convergence rate of the numerical scheme as the discretization is refined can provide valuable insights into the sources of numerical errors and help in the selection of approximate quadrature techniques. Practical considerations and applications. Computational efficiency. Efficient implementation of vector integral computations is crucial, especially for large-scale or real-time applications, as the computational complexity can be high. Optimizing algorithms and leveraging parallel processing can be important strategies. Uncertainty quantification. Incorporating uncertainty quantification techniques such as sensitivity analysis and Monte Carlo simulations can help assess the impact of numerical errors on the final results of vector integral computations, particularly in safety-critical applications. Visualization and validation. Effective visualization of vector integrals, such as through streamlines or color-coded vector fields, can aid in the interpretation and validation of the computed results, helping to identify potential numerical issues or unexpected behaviors. Engineering applications. Vector integrals are widely used in engineering applications such as fluid dynamics, electromagnetism, and structural analysis, where accurate and reliable computations are crucial for design, optimization, and safety considerations. I hope this video was helpful. Thank you.